There are 6 types of simple machines: the lever, the wheel and axle, the pulley, the inclined plane, the wedge, and the screw. Some of these might be construed as repeats of each other. For example, the wedge is basically just 2 inclined planes that are used to force 2 surfaces apart. Similarly, a screw is essentially an inclined plane that's wrapped around a post, but generally we consider there to be 6 types of simple machines. And just to be clear, this picture in the lower right corner is not a picture of 3 screws. That is a picture of 3 bolts, but bolts employ the simple machine, the screw. There are 4 variables with regard to levers. Fe is the effort force. That's the effort that you apply. Fr is the resistance force. That's the force that is transmitted to the machine. De could have 2 meanings. It could be the effort distance, which is the distance that your force moves through, or in the case of levers, it could also be the distance from the fulcrum to the effort force. Similarly, Dr could have 2 meanings. It could be the distance that the resistance force travels through, or in the case of levers, it could be the distance from the fulcrum to the resistance force. There are 3 classes of levers. We can see that the orientation of the effort force, the resistance force, and the fulcrum differs for each class of lever and determines what class of lever you have. You'll also notice that the lever arms are all measured relative to the fulcrum in every case. And down at the bottom I've got examples of each class of lever. Teeter-totter is a first class lever. That's the only lever that has the fulcrum in the middle. A second class lever is exemplified by a wheelbarrow, where the fulcrum is on the outside and the resistance is in the middle. A third class lever could be exemplified by a shovel, where the effort force is applied in the middle and the resistance force is on the outside. The input work in a simple machine is found by taking the effort force times the effort distance. You might recall that work is force times distance. Similarly, the output work is the resistance force times the resistance distance. You need to be careful whenever we use De and Dr in a work equation. They cannot refer to lever arm distances, only distances that forces move. So be careful of that. For example, in this first class lever, if we're talking about the work done by this person, De would have to be this distance here. We could not say that De would be the lever arm between the effort force and the fulcrum. If we're calculating work, De has to be this distance. If we're calculating the work that we get out, then Dr has to refer to this distance, the distance that the resistance moves through. Effort, of course, deals with the force that you apply. Resistance refers to the force from the load. For ideal machines, the input and output work would be equal. That is, FE-DE equals FR-DR. The ideal mechanical advantage is a ratio of distances, the effort distance divided by the resistance distance. Real machines have an output work that is less than an input work. You always have to put in more work than you get out. And that's because some of the work that you put in ends up turning into wasted heat. So the amount of work that you get out in a real machine is always less than the amount you put in. And the actual mechanical advantage is a ratio of forces, resistance force divided by effort force. So the ideal mechanical advantage is a ratio of distances. The actual mechanical advantage is a ratio of forces. As you might guess, neither the ideal nor the actual mechanical advantage have a unit. They are simply numbers. In the real world, no machine is ideal. Efficiency tells how closely a real machine comes to being an ideal machine. It is a percentage. So here are a series of equations, any of which could be used to calculate the efficiency. The output work divided by the input work, or the actual divided by the ideal mechanical advantage, or FRDR divided by FEDE. And then we would want to multiply each of these by 100 in order to put them in a percentage form. For an object being pushed up an inclined plane, the effort distance, dE, is equal to the ramp length L, and the resistance distance, dR, is equal to the ramp height, H. Resistance distance is essentially the height that we would raise this mass to against gravity. For an inclined plane, the ideal mechanical advantage is equal to L over H. If we look at these two wedges in the lower left corner of the screen, the one on the left has a small L to H ratio, which means it has a rather small ideal mechanical advantage. The one on the right has a big L to H ratio, which means it has a rather big ideal mechanical advantage. The bigger the mechanical advantage, the less force you have to exert. You can think of driving each of these wedges into a stump of wood. If we're splitting wood, wouldn't it be much easier to drive in the wedge on the right? The drawback to that is we have to drive that wedge in much farther in order to get the same amount of splitting of the wood. Similarly, if we have two screws here, the one on the left, which has fewer threads, has a smaller L to H ratio. The one on the right has a bigger L to H ratio. The one on the right would be easier to screw in. Think of using a screwdriver and having to screw each of these in. The one on the right, each turn would be fairly easy. The one on the left, each turn would be fairly difficult. The drawback to the one on the right is that although each turn is rather easy, you have to make quite a few turns. As the ideal mechanical advantage increases, the effort force, the force that we have to exert, decreases, but to compensate, we have to make that force work through a much larger distance. Here we introduced simple machines, the 6 types of simple machines, the 3 classes of levers. All lever arms, dr and de, are measured relative to the pivot point, or fulcrum. And we met some equations we'll use in a later lesson. For real machines, the output work is always less than the input work. The ideal mechanical advantage is a ratio of distances, the actual mechanical advantage is a ratio of forces, and the efficiency is always less than 100% for real machines.